Okay, there's something pesky on my screen here now. Okay. All right, we're in business. Okay, so we're going to just do this in part 1 and part 2. Although, who knows, perhaps this part might be better quality. All right, so, so I'm still in the middle of this proof. Okay. All right, so I defined y to have the same signs as the components of x. So what that means is x transpose y, what it's going to do is, it's multiplying corresponding components, it's just going to be the absolute values of all the components of x, since its sign flips where it needs to. But that's the one norm of x. But now we apply the Cauchy-Schwarz inequality and say this is less than or equal to the 2 norm of x times the 2 norm of y. But if y is a vector of plus or minus 1s, what is the 2 norm of y?
Square root of n.
Yes, square root of n. Yeah, Patrick, I might need to pan down a little bit. Okay. So this is square root of n, 2 norm of x. And that establishes that C2 is equal to the square root of n. All right. I used to give these problems of showing norm equivalence as homework, and some of them are terribly tedious. This one wasn't so bad. And no, I'm not giving any of those this time, because they're more interesting problems to give. Okay, question about norm equivalence. Okay. All right. Now, so now that we have vector norms, we can build on those to get matrix norms. Okay, so a function, again denoted by double bars, is a matrix norm on a set of all m by n matrices. If, now the first few properties are exactly the same as for vector norms. So the norm of a matrix is non-negative, and it's equals 0 if and only if A is the 0 matrix. If you scale a matrix by a constant, then the norm is scaled by the absolute value of that constant. And then we have the triangle inequality. Norm of the sum is less than or equal to the sum of the norms. Okay. And then there's another property. Not all books include this in the definition of matrix norms, but it's such an important property that we really should. That if you're dealing with matrices A and B, that makes sense to multiply them. The norm of a product is less than or equal to the product of the norms. And this is known as the submultiplicative property. Okay. Now, it's actually a little tougher to define specific matrix norms than it is vector norms, because if you're not, it's not just a matter of necessarily thinking of the matrix as a big long vector with m times n entries, but vector norms are helpful for defining matrix norms. We just have to go about it differently. Okay. Now, okay. So what we have is an induced matrix norm. So the idea is, if you're given a vector norm, such as one of the p norms, the induced matrix norm is defined as follows, that the matrix norm of A is the supremum over all non-zero vectors x of the norm of A times x. This is a vector norm here, divided by the vector norm of x. Alternatively, you could define it as the maximum over all unit vectors in that norm. So all vectors such that that vector norm is equal to 1. So it's like the unit sphere in that norm of just A times x. Okay. Now, how many of you do not know what I mean by soup? Okay. Soup is referred to as the least, it stands for supremum, but what that means is the least upper bound. Okay. Now, I'm going to get a little unrigorous here, but none of my colleagues are in the room, so whatever. Well, none from the math department anyway. Informally, you can think of soup like a maximum. But the reason why I can't say maximum in this case is we don't have a guarantee that the 2 norm of A will actually be equal to the largest value we can get here. It may be approaching something, like arbitrarily close to it, but it may not necessarily touch it. On the other hand, here, if we just consider all these vector norms limited to the unit sphere in this particular norm, that is a continuous function on a closed and bounded set, so to use 541, 542 terminology, and that is guaranteed to have a maximum and a minimum. And so here it's okay to say max. And in practical terms, we'll often use this definition. But gotta be somewhat rigorous here. Okay. So for instance, any of the vector p norms, we could define a corresponding matrix p norm. So what I'll do is I will show you a few matrix norms of interest, and then we might be out of time, but we'll see. Doesn't really matter whether we are or not. Okay. Actually nicer when it's offline because the webcam's capturing so much more of the board. Okay. Now, so here's some matrix norms corresponding to the specific vector norms I discussed. Okay, so first we have the one norm. Now, the matrix one norm, using the definition, it would be the maximum over all vectors that have a one norm of 1. So in other words, the sum of the absolute values of the components is 1, of A times X. Okay. Now, this definition, of course, is terribly impractical. What we really need is a way to just be able to compute this matrix norm in terms of the entries. We need like a formula for it. And fortunately, we can get one. Because if I write out what this is, oh, this is a one norm, by the way. Okay, so I'll just take a look at this expression. The idea is I need to come up with an upper bound for this. And then I need to show that that upper bound is actually achieved for some x. So I'll look at the one norm of A times X. So that is equal to the sum of the absolute values of all the components of A times X. But now I'm going to use the definition of matrix vector product. So that would be an absolute value, a sum over J. Okay, actually, sorry, A is M by N, so these outer sums need to go up to M. The inner sum goes up to N. So, all right, so if I'm using a definition of the matrix vector product, I get Aij xj. All right. But now what I can do on this sum of absolute values, I can use the triangle inequality many, many times, and I'll get sum over I, sum over j, absolute value of Aij, xj. And what always seems to happen in proofs involving two sums, the key step in the proof is always to switch the sums. It just seems to work out that way. So I'll go ahead and do that here. So I have a sum, j equals 1 to n, Aij, and then I have, okay, so xj, I equal 1 to m, Aij. Okay. So what we have here, notice the index I is changing. In this inner sum, the index j remains fixed. So what this is the j column sum. So what I'm doing is I'm taking all the entries in column j, taking their absolute values, and then summing them up. Now, each xj is being multiplied by the jth column sum. So this is certainly less than or equal to the sum of absolute value of xj times the maximum column sum. So that would be the max j equals 1 to n of the sum of Aij. But this maximum is independent of j. So in fact, I can just pull that out of the sum. But what's left is a sum of all the absolute values of the components of x. And what is this equal to in this case? What's the sum of the absolute values of a vector?
One more?
One norm, but what is the one norm of x here? Because we're taking this maximum.
Oh, it's one,
Yeah, it's 1. Yeah, if this whole thing is equal to 1. Since we're only considering unit vectors in the 1 norm sense. So, 1 norm of A times X is less than or equal to the maximum column sum. All right, so this seems to be a likely candidate to actually be a formula from a 1 norm that we can actually compute. However, we're not certain yet because we need to make sure that is there an X that we can fill in here where the 1 norm of A times X is actually equal to this. So we have less than or equal to. We need to know that for some X we actually hit equal. And it turns out that's not hard to do in this case. What we can do is I can set X equal to EJ, capital J, where J is the column that has the largest sum. Okay. So if that happens, then the 1 norm of AX turns out to be equal to the maximum column sum that I have over here. Okay, so there is an X that gives us equality. So in fact, so this right here is the matrix 1 norm of A. Okay. Down to coast, do you have all that? Okay.
I think so. So you're just trying to put an upper bound on the 1 norm, right?
Right, yeah, we need an upper bound. And as long as we show that that upper bound is actually achieved for some specific X, then we know it's actually not just an upper bound, but the least upper bound. So that is the norm.
Okay.
So what I've boxed here is the actual formula that we would use to compute the 1 norm. And fortunately, it's not hard to do. You're just taking the sums of all the absolute values of the entries in each column, and then you're taking the largest one. Okay. Any questions about that norm before I talk about other norms? Okay. Okay, and the next norm on the list, the infinity norm. Okay, now, in this case, I'm just going to give you a formula, but I can tell you that the way you would prove it is a very similar approach to what he did for the 1 norm. So the definition gives us that it's the maximum over all vectors with an infinity norm of 1. So in other words, all vectors such that the absolute value of the largest component is 1. And then you're taking the infinity norm of A times X. But, again, not practical. The practical formula is instead of a column sum for a 1 norm, it's a row sum. So maximum over all I, and then for each I, you sum the absolute values of all the entries in that row. So in fact, what you can immediately conclude is that the infinity norm of A is always equal to the 1 norm of A transpose, because you're just reversing a sense of rows and columns.
The last one that passed.
Oh, need to pan. Okay. Oh, my line was too long. Okay. All right, I'll keep that in mind. Everybody down there got everything? Okay. All right. Okay, next norm is the 2 norm. Now, unfortunately, the 2 norm is much more difficult to compute for a specific matrix than the 1 norm and infinity norm. There's not a simple formula, but I can give you some expression for it. So, of course, the definition would give you that the 2 norm of A is the maximum all vectors whose Euclidean length is 1. So this really is the unit sphere in n dimensions of the 2 norm of A times X. Now, in order to get an expression for this, I'm actually going to appeal to calculus. So I'm going to define a function g of x to be the 2 norm of ax squared over norm of x squared. Now, I'm defining this function on all of Rn. So in fact, I'm looking at the other way of defining a 2 norm is the supremum of over all non-zero x of 2 norm of ax over 2 norm of x. So you can look at it either way. Yes?
Is it the norm of x?
Yes. Yeah, both norms above and below have to be squared. So I'm going to see how big this quantity can get by varying x over all of Rn. Okay. Now, so it turns out that, so I can write this, when you have a 2 norm squared, that's the same as the dot product of a vector with itself. So I have ax transpose ax over x transpose x, which then I can write as x transpose a x over x transpose x, using the properties of a transpose. So now what I could do is take the gradient of this function, and for that I can go back to the formulas. I believe it was on the second day. No, it was the third day, where I gave us formulas for gradients of these kinds of functions, something of this form. And so if you take gradient of these, you actually have to use the quotient rule. Let's see, do I have time? Yeah, I have time. But what I don't have right now is enough board space. A lot of practice of setting up a laptop in exactly the right location. Okay, so what I need is a gradient of a function g of x. So the gradient of g, actually this is a vector value function, so, all right. Oh, no it's not. What am I doing? No, because this value is a number. So using the quotient rule, it's going to be x transpose x times the gradient of x transpose A transpose x minus x transpose AX times the gradient of x transpose x all over x transpose x squared. Now the gradient of this turns out to be 2A transpose AX. And the gradient of this turns out to be 2x. This is using the gradient formulas at the end of chapter 1, which I still never proved, although we are proved, I believe, in chapter 5 or 6 in the notes. So now if you combine all this, I'm going to factor out some things, because I can factor out a 2, and I can also factor out an x transpose x. So let's go ahead and pull that out. Okay, and what's left is A transpose AX from the first term minus x transpose AX over x transpose x times x. And we want this to be equal to 0 to find a local maximum. Now what we have here, this is a matrix times a vector minus a number times a vector. So it turns out that for a local extremum of any kind, max or min, what we need is x is an eigenvector of A transpose A, and the corresponding eigenvalue is this expression right here, but that's just g of x. Okay. So what that means is g of x, its maximum is the largest eigenvalue, so I use notation lambda max, of A transpose A. Now, admittedly, I have not talked about eigenvalues yet. It's actually the next topic. Although hopefully you're familiar with them from some of our course, but if not, you're definitely going to be. So what we can conclude from this is, since g of x is norm of ax squared over norm of x squared, and that's the square of the expression we're trying to find a maximum of, our conclusion is that the matrix 2 norm of A is the square root of the largest eigenvalue of A transpose A. Although soon we'll see the singular value decomposition, and I'll give an alternative definition in terms of that. Okay. And those eigenvalues are always guaranteed to be non-negative, so we don't have a problem of taking the square root of a negative number. It's not going to happen. The main point to take away now, since we'll deal with eigenvalues on Monday, is this is not something that's easy to compute. So computing a single eigenvalue of a general matrix is not something you can just grind out. There's no specific formula for. So the 1 norm and the infinity norm are much more practical to compute for a general matrix than the 2 norm is. Okay. So any questions about this? Questions from down there?
No, the very top. Yeah.
Oh, this?
Yeah.
Oh,
Can
two.
you,
I'm sorry. Go ahead.
can you zoom up a little bit? Or pan up?
Pan up.
Okay. Oh, by the way, how many of you have gotten into the MATLAB introduction I put out with either MATLAB or Octave? Anybody? Nobody?
What, say that, ask that again?
I sent an email the first week of class about getting started with MATLAB or Octave, and I gave a link to an introduction document.
Oh, yeah, I saw it.
Okay, but nobody's done anything with that yet?
Is it the same one that's on this page for
Yeah.
twice a month?
Yes.
I looked at it.
What?
You're talking about that, wasn't
Oh, right,
it?
yeah.
Actually doing something with that.
Yes.
Oh,
Okay, well, if you have any trouble acquiring, well, Octave's the free one. If you have any trouble acquiring that, let me know. I guess it's probably more difficult for a Mac than for other systems, but you have it now anyway.
Yeah.
So, yeah. Okay. Well, you have MATLAB.
For,
sweet.
What?
for our homework, Dr. Lambers,
Yep.
when you want us to use MATLAB, you're gonna tell us that in the problem, right? It's gonna
Yes.
say specifically, you want us to use MATLAB to do whatever it is you want us to do.
Yes.
Okay.
Yeah, and not every problem is going to have that. Like the probably majority of problems are still going to be analytical. I haven't checked. I don't know. Yeah. Well, I guess you can ask your advisor. He would know. Okay. Okay. All right. So just a reminder to check that out, and especially let me know if you have any problems. Okay. So that's the 2 norm. I have one more norm that's going to be quite useful to us, and this one actually is easy to compute. So it's called the Frobenius norm. Now this norm is different. It's not a p-norm. It is not induced by any vector norm. All right, so we use a subscript of f to denote the Frobenius norm. And all we got to do, it's like what you would get if you took your matrix and reshaped it into a really long vector, and then took the 2 norm of that vector. So you're taking the sum of squares of all of the entries in the matrix, all n by n, summing them up, and then you take the square root. Okay. All right. So it turns out, like with vector norms, matrix norms are all equivalent. So I can write down a few equivalences here, just to illustrate. So for instance, the Frobenius norm of A is greater than or equal to the 2 norm of A, but it's less than or equal to square root of n times the 2 norm of A. Okay. And then a couple other equivalences involving the 2 norm. So the 2 norm is greater than or equal to 1 over n times the infinity norm, bounded above by square root of m times the infinity norm. And since the infinity norm is equal to the 1 norm of a transpose, I have similar inequalities relating the 2 norm and the 1 norm. I just have to switch m and n. Okay. All right, so those are just examples of relationships between certain matrix norms. Now, just as a quick example, if I define a 3 by 3 matrix, 2, 3, 0, 1, 0, minus 1, 0, 4. Okay, so to compute a few norms of this matrix, so first the one norm, that'd be the maximum column sum. So I look at each column. So the sum of absolute values in the first column is 2, and the second column is 3, and then the third column is 7. So the one norm turns out to be 7. The infinity norm, we look across the row. So we have some of the absolute values across the first row is 6, second row is 1, and then the third row is 5. So the infinity norm turns out to be 6. And then one more that is semi-practical to compute would be the, let's see, pen down a little bit. Yeah. Okay. The Frobenius norm. So now I got to take the sum of squares of all these entries. So I get 1, 4, 9, so 14, 15, 16, 16, oh, it's 32. So it turns out to be the square root of 32, so 4 times the square root of 2. Now, so what's interesting is, okay, one norm is 7, infinity norm is 6, the 2 norm is, so 4 times the square root of 2 is roughly 5.6-ish. Okay, and then 2 norm is not something that I would really know how to do, because I'd have to compute A transpose A, so carry out the matrix multiplication, and then compute its eigenvalues, which requires taking the roots of a cubic polynomial and then taking the largest one. And that's something that's a little beyond doing in my head. So, not happening. Although, you can, well, I guess this would be a good time to make a comment about what you can do in MATLAB. So, in MATLAB or Octave, to get the norm of a matrix, if you just do norm of A, so norm is the function, you just pass A as an argument, that gives you the 2 norm, so that is the default behavior. But if you want to use other norms, you can specify using a second argument. So first I could do A1 to get the 1 norm. If you want the infinity norm, you do inf in single quotes. And then finally, if you want the Frobenius norm, you do fro. Okay. So that's how you can get the norms of interest. And MATLAB has certain facilities for timing how long commands take. Like if you just type tick at the prompt and then do whatever you want to do, and then do talk, then it'll tell you how long it took. So I bet if you were to time these commands, you would find that the the 2 norm would take significantly longer than any of the others because it's having to go to the trouble of actually computing an eigenvalue of a matrix. So that requires some iteration, whereas for these 3 norms down here, 1, infinity, and Frobenius, it's just plug and chug. It's just applying a formula. Okay. So, questions about any of that? All right. There isn't much time left. Okay. Actually, I can make good use of these last few minutes. To set up the need for eigenvalues. So I won't actually discuss eigenvalues yet. I'll save that for Monday.
Can I ask one question real quick?
Yep.
So we're defining this notion of distance with norms because we want to. Why are we doing that? Are we going to eventually compare different matrices to see how close they are to one another?
That is one use. Actually, the main purpose I'm about to talk about.
Okay.
Yeah. Yes. Such a mind reader you are. Okay. All right. So it comes back to, again, convergence sequence of vectors. Okay. So consider this sequence of vectors. So what you do is you choose the first vector in a sequence, so x naught, and then each new vector in a sequence is obtained by multiplying a previous vector by A. So where A is some given matrix. This will come up in iterative methods, where if these vectors refer to errors in your iterates, you want that error to go to 0. And you can figure out from your iterative method that the matrix that each new error is a previous error times some matrix, and you can figure out what that matrix is. So if we have this known sequence, well, we want to know if the matrix is known anyway. We want to know when does this sequence of vectors go to 0. Okay. So when does xk converge, not the norm, just the vector itself? When does it converge to the 0 vector? So, but equivalently, the norm of these vectors must be going to 0. Okay. Now, well, first of all, we note that by applying this formula for vectors in a sequence repeatedly, what we get is that xk is a to the k times x0. Because we're just continually multiplying by a. So now we'll take a look at the norm of xk. So the norm of xk, well, that's going to be the norm of a to the k x naught. But using the submultiplicative property of matrix norms, this is less than or equal to norm of a to the k times the norm of x naught. And then I can use that same property, the submultiplicative property, to conclude that this is less than or equal to the norm of a raised to the k power times the norm of x naught. Okay. So, based on that, we can say that xk is going to converge to the 0 vector if what? What condition does the norm of A, if it satisfies this condition, it'll cause these vectors to go to 0. So this quantity here, we want to be going to 0 as k goes to infinity. So what would make that true? So something about the norm of A satisfying what? Anybody? Because you keep raising a number to a power, when will that number go to 0? Yeah, we need to be less. So we want to be less than 1. Okay. All right. So this is one use of matrix norms. That if we have a sequence of vectors such as that generated by an iterative method for solving a system of linear equations, and the vectors in a sequence have this kind of relationship, which is true of iterative methods, that sequence is going to go to 0 if the norm of that matrix is less than 1. So this is a key application of matrix norms. However, what I should point out about this condition is, slightly over time here. This condition is sufficient. However, it is not necessary. It is possible that the norm whatever norm you're using could be greater than or equal to 1, and the sequence will still converge. So what I will do on Monday is show you a sufficient and necessary condition for the sequence of vectors to go to 0. And that condition, necessary and sufficient, can be described in terms of the eigenvalues of A. So that's where we'll pick up. Okay, so
But if the norm of A is less than 1, then it's guaranteed to converge.
yes, that definitely will happen. Yeah, and sometimes it's easier to prove that than any alternative. But yeah, that gives you a little wiggle room. Okay. So I'll have this posted in 2 parts soon.
Yeah, so I had to leave work early today to get a parking detail.